So let's go through and solve it. And what I mean by solve is let's come up with an analytical model for this. Let's come up with an expression for temperature as a function of time based on this particular setup. Okay, so let's start. I'm going to draw this down here. Okay, so there's my little sphere again. And so what I want to do is I want to draw a control volume. I always start by drawing a control volume. So what is the control volume for this problem? Ideas here? Is this going to look, like this? No? Okay. It's going to go all the way around it, like this. So my control volume is the entire object. Why is that? Well, I've already decided that the temperature is not a function of position. There's no temperature gradient that's significant in the R direction. It's symmetric in the other direction. So I can model this entire thing with one temperature. Right? If I can do that, then my control volume is the entire thing. Okay. So what's happening here? Well, we had convection. We have Q dot to the surroundings, heat loss to the surroundings due to convection. And then we also have one other thing happening. We have inside the body, we have a rate of change of internal energy with respect to time. Right? du, U is internal energy. That's changing with respect to time. It's a transient problem. It's stored energy, okay? So let's go out and write our energy balance here. So we're say in equals out plus stored. We don't have any generation, that's why I neglected it there. So n equals out plus stored. Well, what's going in? Nothing. What's going out? Out is Q surroundings, and what's being stored? That's du dt. So if we write out our energy balance, we'll say 0 is equal to Q dot, I guess I call this Q dot convection, which is the same as surroundings here. Let's do this. Q dot convection plus du dt. Okay, that's our energy balance for this. What is U? U, capital U, is equal to the mass of the object times the specific internal energy, lowercase u. Okay, so let's start by kind of expanding out this du dt term a little bit. So du, capital U, dt, is equal to d m times u, lowercase, dt. Okay, the mass of the object is constant, so that can come out. And we end up with, that's equal to m times d lowercase u dt. So this is maybe a little helpful, but we're trying to get to temperature, right? U is not temperature. So we need to get to some representation that includes temperature. Well, it turns out if this is an incompressible object, we can actually write this as follows. So du dt is equal to m times du d temperature times d temperature d time. That's an equivalent way of writing it if this is incompressible, right? If the body is incompressible. This thing here is the definition of specific heat, if you remember from thermo. For an incompressible object, du dt is specific heat. Okay, so we've just figured out a way to transform this to m times c times dt d time. Okay, so that's our u term. In terms of the heat transfer due to Q dot surroundings, right? So we would write that using Newton's law, so which is Q dot convection is h bar times as times t, which is a function of time, minus t infinity, okay, which is also happens to be a function of time for this problem. So we're solving this where t infinity is a function of time. It doesn't have to be, right? You can still have a non-steady state problem where t infinity is a constant. Yeah, question? For this, I'm telling you that's the case. And in a lot of problems, it does change with temperature. And so that becomes a more complicated solution. Yeah, so specific heat is constant, mass is constant. That just simplifies our analysis for now. Okay, so let's see. Let's put this stuff together. So we say what? Let's have to find room here. So dt, d time, plus h bar as over mc times t is equal to h bar as times, or sorry, over mc times t infinity, which is a function of time. Because I just have kind of collected things together. This is just setting those in the same equation and rearranging slightly and dividing through so that we have our highest order derivative is by itself, dt dt. Okay. So then one thing to point out, so we have this quantity here, right? This quantity that's multiplying our temperature. This is actually, if you look at it, we said, what did we say before, that tau LC is equal to R times C, right? If you actually calculate it out, this is 1 over tau LC. 1 over tau LC, that number there. Okay, so this becomes, slightly rewrite it, dt plus t over tau LC is equal to t infinity over tau LC. So kind of a tidy little solution there, ODE. But the tau LC, right, it plays a direct role. So tau LC, unlike BO number, actually is used in the solution. So you need to have the exact representation for tau LC. Okay. All right, so let's see. So let's actually take one more step here, and then what we're going to do is let's introduce the function for t infinity. So writing this out, it's going to be dt dt plus t over tau LC is equal to this function, which we're given over here. Okay, and this function is a0 plus a1 t plus a2 t squared plus a3 t cubed. That's our t infinity, which is a function, and then that's over tau LC. Okay, and then we know, just as to kind of formalize the statement, we know that the temperature at time equals 0 has to equal t initial. Right? That's actually our boundary condition. Hopefully that makes sense. So you're saying, we know it right when this whole problem starts, that our initial temperature is 300 degrees Kelvin. And actually, we only need one boundary condition, right? Because we only have dt dt. It's not d squared or anything. We just have a first order derivative there. And so we only need the one boundary condition. Okay, so this is our mathematical statement of the problem right here. And this is all we need, these two things at the end. Okay, so let's see. How do we solve this? Well, I took the liberty of writing it out already. But if you look at this, we have a non-homogeneous equation. Okay, so we have to go through the same process of breaking this into a homogeneous part and a non-homogeneous part, and then solving those separately. Hopefully you can see, let me just scroll back up, right? You can see that this is a non-homogeneous equation. We've got stuff with t on the left, and we've got stuff that's not a function or multiplying t on the right-hand side. We just have stuff that's a function of time. All right, so we break this out. We'll go through this quickly. So on the homogeneous solution, we're going to say, let's go down a little. We're going to say dth dt plus th over tau LC is equal to 0. That's our homogeneous problem. Turns out actually this is separable, right? This is a separable equation. So we can write it as dth dt plus, equals minus, where are we? Yeah, minus th over tau LC. We're separating out the equation, we can actually have dth over th is equal to minus dt over tau LC. Hopefully you see how I got that. And then let's integrate this. We're going to integrate both sides. Okay, if we integrate the left-hand side, we get what? ln of TH. And on the right-hand side, we get minus T over tau LC plus some constant of integration, C. Okay, hopefully that's something you could do pretty much in your sleep. All right, so then finding the solution for this. So the solution, you could either, by inspection kind of do this, or you could actually, well, by inspection, we just say, let's take the exponential of both sides, right? Kind of see that. Exponential of ln is just the thing, you get the argument. We say th is equal to the exponential of the right-hand side, which is minus t over tau LC plus some constant. Okay, to deal with this constant, exponential of a constant is an unknown constant. So we can actually just pull that out and multiply. Because you remember, if you take the exponential of two things that are linear, you can actually multiply them together separately. If that's not clear, what I'm saying is th is just equal to c times exponential of minus t over tau LC. That's our unknown constant. It's still like exponential of c out in front, but it's an unknown constant, so we can kind of absorb that. Any questions on that? Makes sense. Okay, good. All right, so that's our homogeneous solution. For the particular solution, this is maybe something that's a little different from what we've done before. So dt p dt plus tp over tau LC is equal to all this stuff, right? A0 dot 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 all the way A3 t cubed over tau LC. I just didn't feel like writing it out, but we have that function over there. So what do we do for this type of thing? You can't look at it and say, well, this is a constant on the right-hand side. It's not a constant. It's a function. It's a function of time. So how do we deal with this? Well, the approach was our guess is supposed to be something like the right-hand side, but it would be specifically the thing on the right-hand side and any derivative of that thing on the right-hand side. So what our guess should look like is, what's the right-hand side? Well, it's some cubic function of time. So I'm going to say, C, we'll need a few constants. So C, T, 3. So we have a cubic function we're guessing, but we need any derivative of that highest order thing. So that's, well, t squared, t, and a linear term. That already all appears in that initial solution by coincidence. But our guess just looks like this. We need C, T3 plus another C, t squared plus another c, t plus another c. So let's call this one, I don't know. We have this one will be 2, this one will be 3, 4, and 5. And then this one over on the homogeneous solution, let's make that C1. So C1, 2, 3, 4, 5. We guess those unknown constants because we then have to go through and solve for that. Okay, how do we do that? We go through and solve for that. You take this whole equation here, and let's plug that in for our TP up here. Right, we go through and plug that in, and we end up with the following expression. So C3 plus 2C4 t plus 3C5 t squared plus that second term, which is just TP over tau lumped. So that's C2 plus so on to C5 t cubed divided by tau LC is equal to the right-hand side, which is A0 plus so on up to A3 t cubed over tau LC. Hopefully my shorthand isn't confusing, but we're just writing out the guess for TP by plugging it into the equation up there, and then has to equal what's on the right. Okay, so how do now we've got what, five unknowns, and we certainly only have one boundary condition. So how do we solve this? Okay, so now we're going to use the idea that if, let's say, this equation that I wrote out has to be true for all values of time. If I pick a value of time, all right, pick some value of t and plug it in, this equation has to hold. So if t is changing and t is changing by t or t squared or t cubed, then all of those little pieces of the equation that are, say, linear in t or quadratic in t or cubic in t, they all have to essentially take care of themselves. What do I mean? I mean, we can come up with equations within this equation based on the fact that this equation has to be true for all time. So let's do this for, so let's look at the things that are t to the 0th power. Okay, those things are what? C3 plus C2 over tau lumped has to equal A0 over tau lumped. Or we can come up with an equation just because the things that are to the 0th power all have to be true for all values of time. So if t is changing, that has to be true. You can do the same thing for the first order, which is then 2c4 times t plus c3t over tau lumped is equal to a1 times t over tau lumped. Right? We can do that. We can do the same thing. I'm running out of time. Same thing for the second and the third. Okay, and then we have a system of equations that we can solve for these unknown constants. Okay, that's the method of undetermined coefficients. That's basically as complicated as it gets. So your only task is really to get that guess, right? Get a good guess there. One thing I want to cover really quickly, because you're going to need it for your homework. Oh no, sorry, this will be for next week. So I'm okay with leaving off there. So yeah, any question on this before we wrap up today? Nope. All right, great. All right, thanks everyone. See you Wednesday.